Let's switch gears a little bit here now and talk about the interaction of light. We know how fast it travels, 3 times 10 to the 8. We know how to figure out how fast it travels, maybe a Michelson rotating mirror experiment. But what does it do when it hits something? Well, there's a couple things it can do. It can be absorbed. Light can be absorbed by something. It can be transmitted, keep going through it, right? It goes through glass, goes to the other side. But it can also be reflected. What happens to the reflected portion of the wave? What happens to the part of the EMR that gets reflected? Well, it follows a law, a very clear law, always called the law of reflection. And at some level, you guys know what the law of reflection says already. It says the angle of incidence equals the angle of reflection. Now, you might not know what those words mean right now, but you do. You just might not know it. Everybody's played pool before, right? There's the bumper of a pool table. Maybe for whatever reason, I don't know, there's a ball sitting right here. We'll call it ball number 2. Ball number 1 is right here. And you want to get ball number 1 over here somewhere on the other side of ball number 2. Now, if you're a good pool player, you've got a couple of options. You can jump it over top of ball number 2. Okay, just kind of flick it over top of ball number 2. But the easier way is probably to go around it. Even if you're 10 years old, you might not know how to express the law of reflection. But you know intuitively that if you hit ball number 1 towards the bumper like this, you know that ball number 1 is not going to bounce off the bumper like this. Right? You know that ball number 1 is going to bounce off the bumper more like this, at about the same angle that it struck it at. Now, that is the law of reflection. Knowing that the angle that it hits the boundary at is the same as the angle that it reflects off of the boundary at. Now, we talk about this scientifically. We always define it relative not to the boundary or the bumper of the pool table, but rather we define it relative to a normal line. A normal line is an imaginary line that's drawn at 90 degrees to the boundary. Remember in Physics 20 we talked about normal force? Remember the normal force is the force of the ground pushing up? It really wasn't the force of the ground pushing up. It was the force of the ground pushing at 90 degrees. Remember that? On a hill, the normal force acted like this, right? 90 degrees to the hill. Normal in physics means 90. The normal line is 90 degrees to the boundary. The angle of incidence measured from the normal line, we'll call it theta 1, is going to be equal to the angle of reflection measured from the normal line, we're going to call theta 2. And again, at some level, you guys all knew that. You might not be able to express it this way, but you all knew that the angle of incidence was equal to the angle of reflection. In fact, like I said, a 10-year-old kid would know that the angle of incidence equals the angle of reflection. They just might not be able to verbalize that, that's all. Make sense? This is the basis behind what we're going to do for the next couple of days. Okay, what I'm about to show you now, a couple quick little examples here. First one, really, really easy. Second one, a little bit harder. Are going to illustrate this reflection on its most basic principle. And then we're going to use that to explain some more things, the law of reflection, to explain some more observations that we make. Not just the pool ball bouncing off at the same angle that it struck it at, how to make a good pool shot, but rather what kind of image are we going to see when we look in a mirror? Okay? Maybe not necessarily a flat mirror like we're used to looking in, but why do we see, why do you look short and wide when you look into that curved mirror in the fun house? Or why do you look tall and skinny, or whatever the case may be? Okay, let's take a look at these first. The first one, maybe the easiest physics problem ever. Strikes this boundary, whatever it is, at 48 degrees, reflects. Where's it going to reflect? Well, you better not get this one wrong. Reflects at 48 degrees. Hey, what do you think? This was a multiple choice question. I doubt you'd get something as simple as the first one as a multiple choice, but if you did, what do you think one of the options would be? 48, obviously. What do you think one of the other options would be? How about 42? Okay, we're probably not going to pick 42, but it's 42 degrees right here relative to the boundary, right? That's a number that is relevant. It's just not the relevant number that we want there. All right? What about this one? Let's assume that the boundary between these two mirrors, or the angle between these two mirrors, I should say, is 90 degrees. We want to find the angle at which it bounces off of the second mirror at. So it's going to hit the first mirror at 55. It's going to bounce off the first mirror at 55 degrees. All right. Well, then it's going to bounce off of the second mirror down here somewhere. Where? What's this angle right here? Any ideas? Anybody want to take a guess before we start? Yeah. 55, good guess. Another one? 35. Okay. 90 minus 55 is 35, so that might work. Might work for us. Let's take a look at it. This is 55. This angle right here has got to be 90, right? Because if these two mirrors are 90 degrees to each other, then the two normal lines have to be 90 degrees to each other as well. So that's 90, that's 55. That's going to make this one 35 degrees because all the angles inside a triangle have to add up to give me 180. 55 plus 35 plus 90 gives me 180. Well, then that makes this one what? 35 degrees, right? Good. Make sense? I'm not sure if you're going to get either of these on a diploma exam, but if you do, I would suspect it would be something more like the second one than the first one, right? First one's a little bit, we get some easy questions, but we don't usually get questions that are quite that easy on the exam. All right. We're good, I think, so far. Oh, what's this? This is a mirror. A plain, flat mirror. This is the mirror that you look in a bathroom when you get up in the morning. You get up out of bed at 7 o'clock and you walk into the bathroom and you see how funny you slept on your hair. It's all going sideways and up and all crazy. Okay, this is the mirror that you're looking at yourself in the morning. This is you. You're the object. This is some guy standing in front of the mirror looking at how ugly his hair is or how handsome he is or whatever the case may be. Okay, the top of the arrow is his head. The bottom of the arrow is his feet. Now, this guy, whatever object it is that we're talking about, it could be a guy, it could be a car, it could be a pet, whatever, doesn't matter. It's an object. Or in this case, a guy is the object. I know guys, we're all used to being treated like objects. I'm sorry to treat you like objects even more, but it's part of being a guy, right? Being treated like an object. Our guy is standing in front of the mirror. There is millions of rays of light reflecting off of this guy, this object. They're reflecting off of every part of his body, off of his head, off of his elbow, off of every part of his body, and they're reflecting off of him in all kinds of crazy directions. They're coming from the light bulb, they're coming from the sun, they're coming from any light source possible, reflecting off of him in a million different directions. We're going to draw 4 of those rays, 4 of those rays. Only 4, because that's all we need to predict what the image is going to look like. The first ray of light that's going to reflect off of this guy, we're going to make reflect off of the top of his head. Maybe he's a bald guy. He's got a shiny head. Reflecting off the top of his head. And it's reflecting such that it strikes the mirror straight on at an angle of 0 degrees, right? Measured from the normal at an angle of incidence of 0 degrees. Straight on. Where's it going to reflect? Well, it's going to reflect back upon itself, right? Because if it strikes it at 0, it's going to reflect back at 0 degrees. All right, let's draw another ray of light now that reflects off the top of his head. Remember, one of them reflects straight onto the mirror. Another one reflects down here. There's a million more, but we'll just pick these 2 for now. That's going to reflect off of the mirror over here, something like this, such that this angle right here, the angle of incidence, equals this angle right there, the angle of reflection. Now, those 2 rays aren't intersecting anywhere. They're not coming together anywhere. So we still don't know where we see the guy's head in the mirror. So what we're going to do is actually extend them backwards. Let's extend the reflected portion of this ray backwards. Let's extend the reflected portion of this ray backwards. There's where they intersect. If these two rays of light came from his bright, shiny, bald head, then these two rays of light are going to intersect where the image of his bright, shiny, bald head is. When this guy looks in the mirror, he's going to see himself, or at least so far, he's going to see his head over here on the other side of the mirror. You ever walk into one of those rooms at a gym, like where they do like the, I don't know, like dancing or whatever they do on those Zumba? Is that what it is? I don't even know what Zumba is. What's Zumba?
It's like a dance class workout thing.
Do you do Zumba?
Never.
No. You just.
More.
So okay, Zumba. It's a Zumba room. You walk into the Zumba room, and one wall of the Zumba room has mirrors on it. And you ever walk into one of those rooms, and just for literally a half a second, think, "Holy cow, this is huge," and then you realize, "Oh wait, it's only half as big as it really is, as it seems," because you're seeing the reflection of the real room, right, in the mirror. You ever notice that? When that happens, you see part of the room that doesn't really exist on the other side of the wall, on the other side of the mirror. It looks like it keeps going, even though there's a wall there. Okay? This guy sees his head on the other side of the mirror. When you look in the mirror in the morning, you don't see your head in front of the mirror. That would be odd. That would be really odd if you saw your head on this side, on your side of the mirror. It would be like a 3D movie where the character is coming out at you. You see your head on the other side of the mirror, in the wall, inside the wall. What about your feet? Well, let's draw a couple rays for that. Okay, first ray is going to reflect right off of his feet, straight onto the mirror. Okay, when it reflects off of the mirror, it's going to come back this way. Well, what about the next ray? Well, there's a million other rays, but we'll draw one that goes like this, maybe reflects up like this. This angle of incidence equals this angle of reflection. They don't intersect, so let's extend them back. They intersect right here. Well, those rays came from his feet, so that's where he's going to see the image of his feet. Here's his feet, here's his head, here's everywhere in between. What does he see? Well, he sees the image of himself, same size as his real object, as the real object, right? You look in the mirror in the morning, your head doesn't look bigger, or your head doesn't look smaller. It looks to be the same size. We describe three characteristics, or attributes, we call them. Three attributes, characteristics of the image that we see. And the first one is based on size. In this case, we'd say it's the same size. The image is the same size as the object. If you look into a spoon, one side of the spoon will give you an image that's smaller than the object. Your head is going to appear a lot smaller on one side of the spoon. You look into the other side of the spoon, the caved in side of the spoon, the part of the spoon that you actually use to eat. And if you're close enough to that spoon, then your head is going to seem really big. So the image ends up being bigger than the object. Okay, in this case, it's same size. Sometimes bigger, sometimes smaller, sometimes same size. Second attribute is based on whether it's right side up or upside down. In this case, it's going to be right side up. We'll call it upright. You're not going to look into the mirror in the morning and see yourself standing on your head in the mirror, unless you're standing on your head in the bathroom, which would be odd. You see yourself the same way as you're standing. It's an upright image. Now, finally, the last one. This is the tricky one. Real or virtual. What do we mean by that? Well, a real image is an image that can be projected onto a screen. You're literally looking at a real image right now. A real image that's formed by the projection of light from this projector onto that screen. The image is formed on the screen. You can see the image on the screen. When you go to a movie, same deal. Sometimes you can project an image by a lens or a mirror onto a screen. Sometimes you can't. If you can, it's what we call a real image. If you can't project it onto a screen, in other words, you got to physically look into the mirror or lens to see it. Go into the bathroom in the morning. Okay, what are you doing? You're looking into the mirror. You're seeing the image in the mirror. It's not being projected onto the wall behind you. It's in the mirror. That's a virtual image. Okay, if we can project it onto a screen, it's real. If we can't project it onto a screen, if we got to look into the mirror lens to see it, it's going to be a virtual image, right? Now, how do we know in this case? How do you know from this diagram that you can't see the image on a screen? How do we know that we couldn't put a piece of paper right there or some kind of smartboard screen or whiteboard or whatever and see the image there? Well, here's the rule of thumb. When solid lines are intersecting, and I know I got lots of solid lines intersecting on the left-hand side, but when solid lines of rays are intersecting in certain ways, then we have a real image. Okay? If this ray and this ray intersected, then we'd say that's a real image, but they don't. If this ray and this ray intersected, then we'd say we have a real image, but they don't. Rather, the extensions of them, the dotted lines, intersect. Okay, that's where the image is formed as a result of dotted lines intersecting. That's a virtual image. When dotted lines intersect, it's virtual. When solid lines intersect, it's real. Make a little note there. Dotted lines can't be projected onto a screen. Real image is solid lines can be projected onto a screen. Don't need to project it onto a screen, but it can be. I'm going to take that away, but the good news is I'm not going to require you to write this down. Okay? Everything that's written down below there, we've just done. Okay? I want you to draw the diagram. I want the diagram to make sense to you. And I want you to label what you have to on the diagram so that it does make sense to you. But if you do that, then this stuff down below here might be redundant for you because it just says what we just did.